recording, and we share the screen. I can show any person among you how to do what I have been exploring this semester. And we dealt last time with the clad ballooning, the China syndrome, and we started on the containment structures. And that is going to become an interesting topic. I'll try to explain to you why is it that the Germans, after the Fukushima accident, decided to phase out all their nuclear power plants. Well, they turned into depending on renewables, wind power and solar energy. Solar energy is not successful away from the equator, but wind energy works fine with Germany. They have used up all their land mass over the surface of Germany to the point that they find themselves building wind farms offshore in the North Sea and the Baltic Sea. To the point also that they have switched for their electricity production to coal. And in the news, they're making fun of the situation where they're removing a wind farm just to be able to mine for coal. They also decided not to shut down all their nuclear power plants, but because of they decided to shut them all after Fukushima and to continue using it because, of course, of the crisis that they have in Europe about natural gas that they were importing from Russia. All right, so containment structures. Nuclear power plants are surrounded by containment structures, and those containment structures are maybe 6 feet of concrete. And some people think or spread the word, which is false, that these are enough to prevent the release of radioactivity from the containment structure. I'll make the point today that those containment structures cannot contain the release of radioactivity, maybe for a short period of time, that what we call containment systems are a whole set of engineered safety features that would prevent the radioactivity from being released in the case of an accident. If these systems do not function properly, I don't know how to get you on, Alvaro, then of course radioactivity would be released to the environment. I have to stop sharing and admit you here. So let us see why is it that Germany decided to phase out their existing nuclear power plants. In fact, France has trouble with their nuclear power plants too. They generate 70% of their electricity from nuclear power plants, but because they don't have really fossil fuel supplies, they're very poor in coal and natural gas. But lately, they had to shut down some of their nuclear power plants. Their utility is a government-run utility, EDF. It stands for Électricité de France, electricity of France, because they needed maintenance of their nuclear power plants. So I'm going to argue that our nuclear power plants today in many parts of the world are outdated. They're too old. They operated for 40 years. Nuclear power plants are licensed to operate for 20 years. Then they undergo a license kind of review. They have many of their safety systems upgraded, and they are given another 20 years license to operate. So they operate to 40 years lifetime. However, some utilities are greedy and they want to continue operating their power plants beyond the 40 years to the 60 years. And this is basically a very dangerous situation that people are unaware of. A nuclear power plant becomes, as it produces electricity at a very high capacity factor, very dependable. 90% of the time it is available to produce power. And a typical 1,000 megawatt electric plant would bring in a utility $10 million per day. So it's a cash cow as long as you can operate it safely in that case. So I make the point that it's the engineer safety features that are really the containment for nuclear power plants, not the 6 feet of concrete, and I'll try to make the point for this. This is an actual experiment carried at the Sandia National Laboratory, where they built a replica of a containment structure, and then they brought in piping into the steel outside the containment structure, and then they pressurized the containment on the inside. And sooner or later, you could see here, those seals start leaking. And a 10 square inch kind of opening in the containment can replace the whole volume of the containment within 24 hours. So this is a 22-inch liner here, tear near a containment scale model piping penetration. It's like any chain that would break at the weakest link of the chain. You could see that penetrations. You have piping coming in with the feed water from the turbine plant. You have piping going out with steam again to the turbine plant, and you have piping for the wiring for the control systems coming in and out. And if your containment inside is faced by a leakage of the coolant, and we suggested that the coolant is pressurized in pressurized water reactor to 2,000 psi and to 1,000 psi in boiling water reactors. When that coolant sees the atmospheric pressure, it flashes into steam. So you have two things happening here. First, you lose your coolant, and second, you pressurize the containment. And that pressurization of the containment prevented the operators of the Fukushima plant, as we'll study it in more detail later on, from operating pumps. Basically, the springs on the pumps could not go against the pressurization of the containment. They were unable to release the hydrogen that created the pressure in the containment. And of course, if you have witnessed it, and you can see probably the videos on YouTube, they had the hydrogen exploding, hydrogen explosions, because they couldn't control the release of the hydrogen from the containment structure. So the existing containment structures are not optimal for containing an accident. I'll show you that they'll fail sooner or later if there is no way of cooling any release or quenching any steam release. This is the typical, oops, I lost it. Here we are. This is a typical containment design of a pressurized water reactor. They specify for us here definitely the outside as the biological shield. So that is not the containment whatsoever. This is a shield that is meant to protect the people working on that outside the containment in the turbine plant. And you could see the size of the system here. Like this is a standard man that we add when we do drafting. It has a thickness of about 6 feet of pre-stressed concrete. Inside that containment, you could see that here another shell made out of steel, and they are specifying that somehow in another maybe design that I'll show you, that this is really where the steam that is released in any reactor accidents would be contained. So the concrete shield, as I suggested, is a protection of the internals of the reactor against the outside elements, and that would be because of the curvature of a shell in civil engineering is much stronger on its outside, whereas it's extremely weak on the inside. And I gave the analogy of a little chick breaking the shell from the inside out when it has absolutely no energy, no strength. But from the outside, when we were young, we were challenged to break an egg by squeezing it in our hands, and it's almost impossible, right? So a shell on its outer kind of curvature here can resist extremely high stresses, a Boeing 747 direct impact, as well as acting to protect the personnel in the turbine plant and the rest of the plant here from the gamma rays and neutron radiation coming from the core of the reactor. So here we have definitely a biological shield, and it should be recognized as a biological shield, not a shield against the release of radiation. For this reason, you find here another type of a design of a nuclear power plant. In that case, it's an actual plant called the Sequoia Unit 1, and this is a pressurized water reactor. Notice again the biological shield here, concrete shield building, but they're specifying here, look at this, steel shell. And the steel shell contains the engineer safety features that are the containment itself. And we listed last time the engineer safety features containing the radioactivity for the pressurized water reactor. Today we'll list it for the boiling water reactor. This is an interesting type of a containment structure. It's called the ice condenser. And we'll see that we have as many designs for those containment structures as we have designs of reactor. They're almost like made, they're not really standard. This one here has a system where ice is generated. They call it the ice condenser. So you generate ice and you store it inside the containment structure. Why ice? Because if, say, an earthquake happens and you lose some of the piping, it breaks here, the coolant will be lost. It flashes into steam. That containment would now contain steam at high pressure, and the steam would be quenched or condensed in the ice that's inside the containment itself. This is a part of the design because, in fact, that concrete structure that surrounds the steel shell acts as an insulator. It does not allow the heat that is in the steam that is released inside the containment to be released to the environment. So in that case, it is an insulator, and most of our operating nuclear power plants today are of that design. So if an accident happens, I'll make the point that sooner or later, if you do not provide cooling with the engineered safety features, then you run into a very serious situation like the 3 Mile Island, Chernobyl, or the Fukushima accident. What is not shown in the diagram, well, this diagram, in fact, condenses the steam using that ice condenser, and it has worked so far, so we cannot really criticize it too badly. The engineered safety feature for the pressurized water reactor, I listed here 9 of them, in fact, are not that concrete shield. They are not that concrete 6 feet of concrete of pre-stressed concrete. They are all those 9 engineered safety features, as we call them. The control rods, the containment vessel itself, it has a containment spray system to quench any steam other than the ice condenser design. The accumulator tanks contain water under pressure, 20 atmosphere. If the coolant pressurization falls below 20 atmospheres, that nitrogen automatically injects water into the reactor structure. There is a residual heat removal system, heat exchanger. Remember, we said that nuclear power plants have an interesting feature that does not exist in conventional boilers. In the case of the generation of decay heat from the radiation of the fission products, that has to be cooled for at least 24 to 48 hours. When the system has an accident, initially it's at a high pressure. So in that case, to bring in water for cooling the system, extracting that decay heat, you need a pump that can generate a pressure of 100 barometric or 100 atmospheres. But if you design a pump that generates very high pressure, you find that the flow rate of the pump is very small. So the operator would have manually to depressurize the system. And in that case, they have not a high pressure coolant injection system, but a low pressure coolant injection system now that operates at 30 atmospheres. And because the pumps here are operating at a low pressure, then you can have a much larger mass flow rate in cooling the system. Suppose that your control rods cannot come into the core, you'll find that you have a tank that contains boric acid and boron is a very strong absorber for neutrons, so it would be injected in the core to shut down the chain reaction. Now, in the PWR, the pressurized water reactor, that injection of the boron is automatic. The automatic control system injects the boron, replacing the control rods. But in boiling water reactors, for a while, in older designs, it has to be, the operator basically has to initiate it. It has to be initiated by the operator. And then an excess supply of water for the refueling water storage tank is available for the cooling of the containment. Most containments for PWRs and BWRs contain a spray system. You could see here, this is the steel structure. Now, we are not even showing here the concrete structure. People think, oh, the concrete structure is going to contain radioactivity releases in an accident. No way. You could see here that there is a provision here of a containment spray. It sprays water, getting water from RWST. This is what I mentioned a few seconds ago, the refueling water storage tank. It sprays the containment, and that water contains something that would neutralize the iodine that would be released in that type in the containment structure. So sodium iodide, for instance, would be used. It interacts with the iodine, or potassium permanganate, any chemical that would quench the steam. The quench steam goes to a sump pump at the bottom of the reactor. I'm showing it here because it played a role in the 3 Mile Island accident. And then you take the sump water to a heat exchanger to cool it and re-inject it back into the core. So you could see here that if you do not succeed in quenching the steam, sooner or later, I'll make the point that radiation would be released to the environment. So what are the functions of the essential equipment in the containment structure? First, you have the containment spray isolation valves. And when you get accidents where the core is heated to a large degree, and that is what happened in the Fukushima accident as well as in the 3 Mile Island accident, you have steam now interacting with the cladding that contains uranium dioxide fuel, which is a ceramic. It can take 2000 degrees Celsius temperature, but the cladding itself interacts with the steam. And in that case, you get the cladding basically oxidizes, it burns with the oxygen in the water, and what you're left with is hydrogen. So in those accidents where you reach very high temperatures, you can generate hydrogen. And we know that hydrogen is extremely reactive if it has access to oxygen. It can react in an explosive way if it is not controlled. So in that case, you find that containment structures contain hydrogen igniters. In the case hydrogen is released, you burn that oxygen or hydrogen recombiners. What you do is use what's called the sparging process. I'll show you a diagram for it. You let the hydrogen bubble in water, and then on the surface, you ignite the hydrogen in a controlled fashion using maybe a spark plug from a car. Just a spark will burn it. Those recombiners caused our nuclear power plant here at Clinton to be delayed for a whole year of construction when they had to add those hydrogen recombiners, and it delayed the construction for a whole year. You have hydrogen mixing fans and compressors, hydrogen mixing valves, and so on. And unfortunately, as I mentioned, at the Fukushima accident, the pressure in the containment was so large that those valves that would release the hydrogen to the atmosphere could not function. The springs did not overcome the pressure in the containment. When we study the Fukushima accident, we'll bring that into attention. You have to also use a low pressure coolant injection system to provide the containment integrity. So if you lose your coolant, and the main design basis accident for PWRs is really a break in the coolant lines, a guillotine break, meaning that the pipe is opened on both sides, losing the coolant, and coolant that is pressurized, like if you open up the cap on your radiator, it sees the atmospheric pressure, it flashes into steam. So it's a loss of coolant as well as generation of steam. To maintain the core in a safe condition, the reactor pressure level and pressure transmitters have to operate. And then after the accident, if the accident happens, you have to use the hydrogen sensors, use pressure transmitters and temperature transmitters to monitor the accident. The supporting equipment obviously are the power cable and instrument cables. This is what's called the sparging process that delayed the construction of the nuclear power plant next to us for a whole year. They had to add that equipment that was not planned initially. So you simply get the hydrogen and you bubble it underwater, and on the surface you allow it to burn. It will burn in that case in a non-explosive matter, like what happened in 3 out of the 4 reactors included in the Fukushima accident. The fact that was ignored in the Fukushima accident design is that there was a pulse that was detected earlier on, much earlier on in the 3 Mile Island accident. They detected that pulse here, you could see here, and a stress spike, and they think it was basically caused by a minor hydrogen explosion, not at the same level as what happened at Fukushima that destroyed the whole structure around the plant itself. Now, I want to make the point and explain to you why is it that the Germans, after Fukushima, decided to retire their nuclear power plants. And I think they're smart people. They made their decision in an engineering conscious way because their plants were all old and they would not be able to take a situation like Fukushima. We have the same situation, unfortunately, in the United States. At least I'll tell you what kind of remedies we are trying to do to access that situation. These are plants here that have different designs of containments operating in the United States. And you can go and check the reference here, reference 1, from the report from the Nuclear Regulatory Commission. In Zion 1, unit number 1, the technical specification is that the containment can take a pressure of about 149 PSIA, that's pounds per square inch absolute. Beyond that pressure, basically you cannot be sure that you will be able to maintain the radiation that would be released inside the containment from leaking to the environment. Look here, that what is the best time to failure with unlimited water in the cavity of the containment? 16 hours only. So within 16 hours, if you do not quench that steam that produced the high pressure 149 psi in the atmosphere, then of course your containment will fail. And that is established. Basically, you get earlier failure, physically unreasonable best estimate pressure rise, including the heat sinks. Surrey, another reactor, the containment capability in that case is 135 psi absolute. If you do not provide cooling, you get several days where you can contain the radioactivity, but sooner or later, within several days, it will leak. They don't give us complete detail, but Sequoia is another plant. They say that the technical specification that the failure of the containment, which is a concrete shield there, is quite likely. Browns Ferry, oh, quite likely. Limerick, rather, that one they say rather unlikely. Grand Gulf is another plant. You get pressurization failure from diffusion flames. So what they mean here is diffusion flames out of the ignition of hydrogen generation. Some plants are better designed than the others. It can take 75 psi of pressure. SP1 accident comparative results, you'll find that early failure, 100% core dispersal, meaning that all the radiation in the core would be dispersed as the environment, 100% clad oxidation. Let me explain to you again that clad oxidation. In chemistry, one way of producing hydrogen, if you want to produce hydrogen, that one doesn't work. It's very simple. If you get water and you run it on hot iron, this would be steam on hot iron, you'll find that the iron, obviously here, would oxidize. You can say it's burning, right? Oxygen with iron it's burning, but let's say it's oxidized, and the equation tells us very simply that you release hydrogen in that case. Now, in nuclear power plants, we use an alloy of zirconium. So the cladding, so that's H2O plus zirconium. If you have that high temperature steam interacting with the metal, you burn the zirconium, you oxidize it, and the zirconium oxide is basically powder. So it falls off. So you'll find that now the fuel does not contain the cladding that keeps the radioactive element inside it, and the radioactivity is released to the environment. Not only that, but then you get also the hydrogen, and the hydrogen is highly reactive. It can burn, or it can even explode, and we have seen the explosions in general. All right, so let us study the modern containment designing aspect. So what do we do about this? People have recognized then the existing generation of nuclear reactors, particularly the Germans, as well as Sweden, I think to a certain degree, cannot get protected against the release of radioactivity. So people have been thinking about alternate designs, and those designs, in fact, are licensed and they're being constructed, for instance, in China and in the European community, in France and in Finland. And so the company from Japan, Toshiba, that purchased the American company Westinghouse. So Westinghouse is located in the United States, but it is a subsidiary of Toshiba. Westinghouse itself was owned by a public company in the UK, in England. It was called British Nuclear Fuel Limited, BNFL. So basically, both Westinghouse and Toshiba have come up with a design that should be an evolution of the existing design that you have in the United States. And you'll see that some of the design features support the claim that existing containment structures are not good. And basically, these are accidents ready, waiting to happen. The design that came out is designated as Generation 3+ nuclear power plant, because that's the third generation of nuclear power plant, but it's an evolutionary design. And they name it the AP1000. AP stands for Advanced Passive, because we'll see later that if you get an accident, most of the time we have as engineers expected it. But when accidents become serious, it is because a sequence in the accidents occurred. And we have mentioned that earlier in other lectures. For instance, you get maybe an earthquake that causes a tsunami, but then somebody makes an error, a human error, and then you may have a design flaw following it, and then you may have an equipment that fails. Then it becomes beyond design basis accidents that we cannot foresee beforehand. So we want something that would be safe in a passive way without the intervention of the operators, at least eliminating the human error part. So AP1000 stands for Advanced Passive 1000. That's 1000 megawatt electric. And they have a version of it that's called the AP600. So the design in that case is shown here as an artist's conception. You notice something important in the design is a big, big chimney there on top. And I'll show you details of it. And look at those holes also in the containment structure. This is an artist's conception by Toshiba Westinghouse. It seems that Japan is, of course, depends also on on nuclear energy for its electricity. After Fukushima, they depended for a while on natural gas and coal, but they're coming back into recertifying their nuclear power plants. This is how the detail of that containment structure now in the AP1000 is built. Notice again, as I told you, that it is really the steel shell that protects against the release of radioactivity, and you have to cool that steel shell. If you depend only on that 6 feet of concrete, it is an insulator. You don't allow the heat to be released to the environment. So what they have done in that design is that they provided that big chimney on the top, and that chimney here contains water, a big, big tank of water. In the case of an accident, that water would be dripped on the steel containment there inside the concrete shield. So the concrete shield is not there as a containment. It's more like a biological shield. As the water drips on the steel structure here, it evaporates, and as it evaporates, it takes the heat out and is exhausted from the chimney there at the top. So where do we get the heat there? You'll find that those holes that I have shown you allow air to circulate from the top to the bottom and then rise again to cool the containment structure. So in that case, we eliminate the existing design flaw in most nuclear reactors in operation today, where the containment acts as an insulator against the release of heat to the environment in general. So you could see here, the cooling is enhanced with a tank on tank. That should an error here. That would be a K here on top of it, containing a supplemental water coolant supply. And this is a reference from Toshiba Westinghouse. Another design that is being built, in fact, in France and in Finland, 2 units are working along the same way, is what Areva, this is a French company that actually it was named earlier on Framatome, for France Atom, and it was owned by Westinghouse, but then it became independent by itself. So it is building nuclear reactors for France and for other European countries. So they name the design that they use as the EPR. Some people call it EPR for the European pressurized water reactor, the E, and some people call it the evolutionary PWR. And it seems that 40 years is a long time for operating the old designs of nuclear power plants. We need really to adopt the new designs. The EPR is designed by Framatome in France to provide a high level of safety, and particularly on the probability not of a pipe just breaking, but for the accident to proceed even further, where the core would melt down. And if the core melts down, you get a mixture of the fuel melted out, the uranium dioxide, you get the cladding melted out, you get the control rods melted out, you get the spacer for the fuel elements inside the core also melted out. The whole thing is a mixture of a molten metal, and the name for it is a corium material. If you look at some of the details of the Fukushima accident, as we'll do, the TEPCO company, Tokyo Electric Power Company, shows us that some core meltdown, in fact, happened in their plants, and the water leaked from the bottom of the core. They had boiling water reactors in that case. And as we have described in the steam explosions kind of phenomenology of reactor accidents, a molten metal interacting with water can cause a deflagration and basically an explosion. And that was tested in the borax experiments that I have shown you earlier. So this is a design that Areva now implements in the designs of their PWR. You notice here 4 heat exchangers for high reliability, not just one. If one of them failed or 2 failed, you still have 2 more to cool the plant. But the important aspect of the European PWR, or the evolutionary PWR, is what's called the core catcher. And this is some detail about the design here. They suggest that if your core melts and it's molten metal, it could go through the pressure vessel there at the bottom and leak. And they don't want it to get into the ground and interact with the water in the concrete. If that molten metal interacts with the concrete in the base mat of the reactor, it can release lots of steam first, because we cure concrete with water. It will also release hydrogen. So what they do is that they have a core catcher where they would catch the molten core material, the corium material, and spread it in a pond with a large surface area to radiate its heat to the environment. This is not going to happen every day in the design, but these are all engineered safety features that would mitigate the possibility of more serious accidents in general. So in that case, we see that there are already many ideas on how to build evolution in nuclear power plants that are safer than the existing fleet of nuclear power plants. It is very obvious that the Germans discovered that their power plants were not safe enough, so they have basically decided to shut them down. Most of the reactors, the 6 reactors that were at the site of Fukushima, 2 of them were not operating, 4 of them went extant. All of them were basically boiling water reactors. And as I'll show you, most of the fleet of reactors in Germany and Sweden are also boiling water reactors. In the same way that the pressurized water reactor has its own engineered safety features, you'll find that the boiling water reactors have similar engineered safety features, but there is 2 differences there. The control rods is an engineered safety feature, same as a PWR. The containment spray system, same safety feature as the PWR. However, boiling water reactors have a pressure suppression pool. So that's a large pool in a toroidal shape at the bottom of the core of the reactor. By the way, I'll insist later on that it's the wrong position to place it. But the pressure suppression pool would have the steam that is released, say, from a break, from an earthquake, from the piping in the containment structure. That steam would be bubbled into the pressure suppression pool to prevent the buildup of pressure in the containment. And we said that the buildup of pressure would eventually, within maybe 24 hours or 48 hours, fail the containment structure. They still have a residual heat removal system, heat exchanger, or what we call the after heat or the decay heat. They have a high pressure coolant injection system. Initially, the pressure in the reactor core is very high, so you cannot inject water unless it's a high pressure, but at a low flow rate. Then you depressurize the system intentionally. You could see here that it is not passive. The operator has to depressurize the system, then he gets a low pressure coolant injection system into action. A boron injection tank to replace the control rods. If the control rods basically as a result of clad ballooning, remember the clad ballooning chapter, then the control rods cannot be inserted. So you simply flood the core with boron. And you have an excess supply of water in what's called the condensate storage tank. This is the same as in the PWR as the refueling water storage tank or the accumulators. And BWR have a very interesting feature here that is very questionable, especially in the Fukushima accident. If the temperature in the core increases beyond the limit where the core, the water in the core has boiled out and the core is uncovered, I gave you a problem for the loss of coolant accident, the time that it takes a core of 1 meter, say, in height to be uncovered is seconds, minutes maybe, but not too long. So in the case of the BWR, they have a system that sprays the core in the case of the water boiling off the core to keep it cooled. Otherwise, they'll get that nasty reaction there where the cladding burns out or basically turns into a powder by oxidization. So they have a system that sprays the core if the water level in the core has fallen down. And this is a system that is very questionable because here you are going to be spraying a core that is at a very high temperature with steam or liquid. And you are encouraging that reaction here. And apparently that reaction may have happened in the Fukushima accident leading to the production of the steam, but it is kept under a tight lid in addition to the possibility of a steam explosion. So this is the advanced boiling water reactor that the General Electric company tries to build today. You notice here that you have the pressure vessel right here. I lost my mouse here apparently. Oh, here is the pressure vessel. And the water supply, the pressure suppression pool is a toroidal shape here around the bottom of the reactor where, say, a safety relief valve SRV here would relieve the pressure if it increases beyond the design pressure and quenches it in the water in the pool. Notice that under the core of the reactor itself here, you have what's called the dry well. This area should be dry. And when we studied the Fukushima accident, they had a design flaw. The design flaw was that they had their pressure suppression pool water right under the reactor core. And that means what? It means that if the core melts down, it would interact with the water, leading not just to the generation of hydrogen, but to the steam explosion that we tried to model by application of the conservation of mass, of energy, and momentum, the basic equations of fluid flow. It turns out that maybe also in the Fukushima accident, the core in one at least of the reactor unit number 1 may be melted, and the control rods not shown in that diagram come in from the bottom from boiling water reactors. So the core material was able to escape, and that lower dry well was not dry, had water in it now. So they had a monumental steam explosion that I described in the chapter on steam explosions, the 2 lectures ahead. All right, so let us see what are the containment structures. It seems that so far the designs in the nuclear industry has been for each different power plant, some kind of specialized design. They don't have any standardizations whatsoever. So you'll find in the United States, we have 3 kinds of containment structure. I already mentioned this one here, number 3 here, the ice condenser. You'll find that 13% of the nuclear power plants operating in the United States have that ice condenser. Here, a factory basically producing ice inside the steel containment. They call it in the diagram the primary containment, the steel structure, the steel shell, I should call it. And around it, the biological shield has the name, the secondary containment. So they call it primary containment and secondary containment. In some designs, which is what's called the subatmospheric containment, this is 9% of the reactor operating in the PWRs. I specify here, PWRs in the United States. It's a totally, it doesn't have the ice, obviously, but you still talk about, they still have considered the steel shell, steel containment liner. So you have the liner inside the concrete shield or the biological shield. And 78% of the reactors operating PWRs, pressurized water reactors operating in the United States, to the left here, are basically totally dry containment, no ice condenser, and large dry containment structure whatsoever. They don't even mention the steel shell, but is not shown here is the spray system in the 3 designs. So this is the containment structures in the PWRs, pressurized water reactors in the United States. This table shows here the detail about it. The large dry containment, the ice condenser, the subatmospheric, that was by 1986, they have 15 of those reactors. The reinforced concrete, 8, 2 for the ice condenser, 6 for the subatmospheric, and post-tensioned concrete. It turns out if you had classes in civil engineering or maybe in some in civil engineering, and you learn about concrete, you know that concrete is strong under compression. If you compress concrete, it can take the compression very easily. But if you expose concrete to tension, it would flitter apart, fall into pieces very easily. And that's why we use what's called the post-tension concrete. And in fact, if you noticed how the constructions of roads is made, you have a road with a layer of concrete on the top here, but at the bottom you find steel bars under the concrete. So concrete here takes the pressure from the wheels of the trucks or the cars and is now under compression. It can take that compression, but when you add the steel, we know that steel is very strong under tension. So you combine the tension of the steel and the concrete, and you get a structure that's stronger than concrete and stronger than steel. So that is what's called pre-stressed concrete. Actually, what they do is that they get the concrete like this, and then they put in steel bars in it, and they put bolts here and bolts here and bolts here and bolts here, and they compress the concrete by turning those bolts into some kind of a thread here. So when you compress the concrete, and the symbol for concrete, as you have seen it in many of your drafting classes, maybe, you pre-stress the concrete, it becomes stronger than concrete that is not pre-stressed. So those containments are pre-stressed concrete pressure vessel or post-tensioned concrete pressure vessels. And again, here I show you more detail of the ice condenser design that is basically built by the Westinghouse and Toshiba company. Now, if we go and try to explain why is it that our friends, the Europeans, have as designs, this is the design that they have in Germany, and that's a PWR, 920 megawatts, and you could see they give it a shape of a sphere so that they would equalize the compression or the stress around the steel shell. Notice again here, what I'm emphasizing today is that what contains the radioactivity in reactor accidents is really the steel shell. And this is a concrete containment on the outside. And I hope that I can convince you that this is the case. This is another design in Germany. In that case, it's a PWR. And you could see again the steel shell here separate from the concrete biological shield. And the Germans had more boiling water reactors than PWRs. And they show you here a boiling water design, a steel shell here. And they know what they're doing. They say, oh, the steel shell is really the containment. But the concrete on the outside is a shield building. It shields against radiation and protects the environment. Notice here also that the design has a dry well, so the water is surrounding the bottom of the reactor core and nothing below the reactor, because they would expect that steam explosion to happen. In the United States, we have 29 boiling water reactors there with different designs of the post-tensioned concrete and reinforced concrete where you have steel, but post-tensioned is when you put in those bars and then you tension them, you put the concrete under compression, it becomes much stronger under compression. Now, this is the design that is called the light bulb design. That's one of the very early designs of boiling water reactors. I'm showing it to you here because that is the design that we are studying in more detail for the Fukushima accident in that case. You notice that we mentioned that the difference between the PWR and the BWR is that large torus pressure suppression pool. And you could see here that if there is a break in the piping inside the light bulb steel containment that would be surrounded by the concrete containment on the outside, you find those pipes getting the steam generated in the primary containment, quenching it in the pressure suppression pool. Now, I contend that this is a flawed design. And in fact, some of our students in a research project, that term project really addressed it. This pressure suppression pool is not positioned at the right place. Why? If you would position it on the top there, you would allow the water that heats up inside the reactor core to rise just through natural convection. We know that hot water has a low density, so it rises up, and then it could come down back again to the pressure suppression pool, and you don't need the intervention of operators because you get natural circulation to occur. So I think this should be a feature in all future boiling water reactors, rather than having the water at the bottom of the plant itself. This is the designs of the Mark II design. Notice they replaced that steel structure by simply concrete structure where you have the water away from the core where the molten material can interact with the water. So that is in fact the design for the Fukushima accident, the light bulb design. And unfortunately, that area apparently in one of the units, unit number 3, filled up with water, the core melted, interacted with the water, and we may have had a monumental steam explosion. So still the design has a pressure suppression pool here. That's the core, the pressure vessel of the reactor in advanced boiling water reactors from the General Electric companies. This is another design again, but that is a flawed design. I would not accept it to operate it because you could see the water here under the core. That is possible setup for a steam explosion, and that is not acceptable for operating existing power plants that have that particular design. Under the core, you must have a dry well. And these are, again, designs in Europe. These are designs for plants in Germany. and designs in Sweden. And the Germans decide to basically that their designs are very old. Look here at the level of water surrounding the pressure vessel. Steam explosions can happen in that case. There are designs where you try, by Sweden, I think, where you try to filter the containment atmosphere into beds of sand and fine sand here and gravel before releasing it to the environment. That is a Swedish filter design. They take the atmosphere from the containment structure and release it through gravel filters before it's released to the environment. Bad design here too. You don't place water under the core where the core can melt and cause a steam explosion. Very quickly then to close that chapter here, a misconception about nuclear power plants that I would like you to learn about is that the containment structure is that the concrete construction. Such a task of containment is done by the engineered safety features, not by the biological shield. So they're being replaced by evolutionary designs where the core maybe in the EPR is spread in a pool, and by the AP 1000 where now you try to cool the steel shell rather than have the containment act as an insulator. A suggested more logical location for the pressure suppression pool in BWRs also should be above the core, not below the core. Why is it below the core? Well, maybe it's easier to construct it this way, but it doesn't provide us with the level of safety where you avoid the human error by the operators in general, and the system would cool itself by itself. And this is a suggestion for the design of future boiling water reactors. And at that, I wish you a nice weekend. Thank you for showing up, and read the